Namaskar and welcome to lecture 37 of this course on hydration, porosity and strength of cementitious materials, and today we will concentrate on the stress strain behavior of concrete. That is, how does concrete behave under applied stress. This is our familiar slide where today we will try to model the behavior of this concrete which has been viewed like this under the action of stress. The stress strain curve is an important engineering property of any material and yields very significant information including the modulus of elasticity. In case of concrete, the stress strain curve in compression is of primary concern, and that is what we will focus our attention today. On the left hand side here is given the stress strain curve of the cement paste, the aggregate and the concrete. That is what our model. So, if we look at cement paste and aggregate, the stress strain behavior is largely linear, which is not the case for concrete, and that is something which we need to talk about and discuss in detail, and that is what the idea of the discussion today is. We will basically discuss the stress strain behavior of concrete in compression, and we will talk about how the modulus of elasticity of concrete can be defined, including what the codes and specifications and methods of design help us do, how it can be determined, how it is normally determined, and also how designers estimate those values in design and what is the guidelines that are available to us in different codes and specifications. Now, this concrete here is having a lot of micro cracks in the HCP for all kinds of reasons, and that is something which we have talked about when we were talking about the constitution and the formation of the hydrated cement paste. So, these micro cracks are present in HCP of concrete prior to the application of external load. So, these cracks are micro cracks, very small, not necessarily connected with each other, but they are part of the concrete to begin with, and that is, these are not formed on account of load application. These micro cracks could be due to differential strains between aggregates and the matrix, that is the hardened cement paste. When exposed to normal atmosphere, drying or thermal shrinkage effects, these cracks are stable at low levels of stress. But as structural cracks are formed in the concrete, these micro cracks also obviously become involved in the whole process of crack propagation. They also play a part when we talk about crack initiation in the concrete. This business or this subject of cracking is in fact a fully developed subject in its own right, and we talk about fracture mechanics, which deals with the formation and propagation of cracks. We are not going to look at this crack formation from a fracture mechanics point of view, but you must know that those of you who are interested to understand this whole idea of cracking in solids, fracture mechanics is something which will help you understand that aspect a lot better. Today our concentration of course is on the stress strain behavior, which gets affected by the presence of these cracks. And at higher levels of stress they are unstable, resulting in rapid crack propagation. Now, with this kind of a backdrop, we look at this picture once again and we find that unlike aggregates and cement paste, concrete is not an elastic material. The stress strain behavior of concrete becomes curvilinear at higher stresses. Initially, yes, we can assume or we can see that the behavior of concrete is also quite linear, but does not remain linear at higher levels of stresses or strains. Researchers explain this non-linearity from the point of view of progressive microcracking in concrete under the action of loads. I would like to draw your attention to this particular graph, which is of course only an illustrative example, it is only a case in point, and we find that if the ultimate load carrying capacity is about 30 to 33 MPa, the linear portion is only about 10 to 12, which is about 1/3 to 1/4 of the overall capacity, the ultimate strength of concrete. And this is something which we need to understand or keep at the back of our mind when we move forward in our discussion. Now, this is an illustrative example of how we would like to discuss the stress strain behavior and the modulus of elasticity of concrete. This picture shows stress and strain, and the stress levels have been divided into 1, 2, 3 and 4, where level 1, level 2, level 3 and 4 are given in terms of percentages of the ultimate strength. And that is exactly the kind of thing which I was alluding to when I tried to draw your attention to the stress strain curve of concrete in the last slide. Now, moving forward with this, the slope of the stress strain curve of concrete under uniaxial compression, that is what is shown here. Due to the non-linearity, besides the dynamic modulus of elasticity, three types of static moduli are defined in this context. One is tangent, the other is secant, and the chord. We will come to this when we come to the definition and the estimation of the modulus of elasticity of concrete. Now, continuing with our discussion on the stress strain curve, stage 1, we have a load level of about 30% of the ultimate stress. We can assume, or we get more or less a linear elastic behavior as far as concrete is concerned, and that is characterized by microcracks remaining stable and undisturbed. So, this picture here is that of concrete with aggregates suspended in our HCP, and so long as the load does not exceed 30% of the ultimate strength, whatever microcracks are present in the HCP, they remain stable and undisturbed. However, when it comes to stage 2 and we start reaching about 50% of the ultimate load, the microcracks begin to increase, but that still is a stable system of microcracks prevailing in the HCP, and no cracking occurs in the mortar matrix. The curve deviates from the straight line. And when we come to stage 3, where the stress applied is closer to 75%, or it's between 50% to 75%, basically exceeds about 50% of the ultimate stress, the crack system in the HCP tends to become unstable and the rate of crack propagation increases. That is the time when cracks begin to form in the matrix and the stress strain behavior is truly nonlinear. Progressively, when we get into stage 4, where the stresses are closer to failure, there are very high levels of strain, and that increases. There are very high levels of strain, due to which the crack system becomes continuous in the HCP and the matrix. So, these pictures here on the left hand side show how we can visually represent the formation of cracks in the concrete as we apply higher and higher levels of stress. So, it is very interesting to visualize that a concrete specimen, when subjected to load, behaves linearly to begin with when the microcracks remain stable, which is when the applied load levels are less than about 30% of the ultimate strength or the capacity of that concrete. As the stress levels increase, the microcracking increases, causing the behavior to become nonlinear, and finally we have a complete disintegration of the concrete with the formation of larger cracks. Now, with this background, let us go and see what kind of stress strain curves are prescribed or available to us in different codes and specifications. What we have seen earlier is the actual experimentally determined stress strain curve of concrete, which is carried out in the laboratory using a concrete specimen. Now, in a lot of cases, it may not be possible to carry out that kind of a sophisticated experiment to determine the stress strain curve of that concrete or to study the stress strain behavior. Also to facilitate design across different structures and different designers, the codes of practice, for example the IS 456, give us certain idealized stress strain curves of concrete in compression. So for IS 456, it says that up to a strain value of 0.002, the variation can be taken to be parabolic, and following that it can be assumed that the strain will increase without any change in stress. And that is what is depicted here, and it is not our intention to discuss the design aspects of the stress strain curve. The difference in my intention was only to introduce to you the fact that idealized graphs are available in codes and specifications to help us evaluate the level of stresses and strains at different locations and so on as far as the concrete is concerned in a RC member. Now, other than the IS, this picture here shows the Japan Society of Civil Engineering guidelines for structures. I should say a more or less similar graph where there is a curved portion and a flat portion. Of course, these values may or may not be exactly the same as given in the Indian standards. So this really shows that different standards adopt different details as far as any aspect is concerned. Of course, in this case we have taken up the idealized stress strain curve, but that is true more or less for any parameter. If we compare it across different codes, we will find certain differences, but the principle more or less is quite similar. Now, one of the most important information that comes out of a stress strain curve is the elastic modulus or the modulus of elasticity. Now, for a linear material, if we plot the stress strain curve, the slope of this line does not change depending on the location, whether we talk of stresses or we talk of strains. In the case of a non-linear material like concrete, as we see here, the stress strain curve is changing its slope at different levels of the applied load. In a situation like this, how should the modulus of elasticity be defined and used as far as calculations are concerned for deformation, deflection and so on and so forth? Codes tell us secant, chord. We can talk in terms of the secant modulus, the chord modulus, tangent modulus and the dynamic modulus, as we will discuss now. For calculating the elastic modulus of concrete, if the final strength is 26 MPa, as we can see from here, we decide that let us take 40%, and that helps us define this point S. That is, for this non-linear curve of the stress strain, we take 40% of the ultimate strength and try to find out whatever the strain value is at this point. The second important point in this graph is a 50 microstrain point, where we go up on this stress strain graph, stress strain curve, and find out what is the stress level corresponding to that point. Now, beginning with this point 1, this point 2 and the third point, which of course is the origin, let us try to define what is the secant modulus. Now, the secant modulus given here corresponds to the slope of the line S0. That is, from the origin we take this point S, and even though it is a curve, we say that this is my origin, this is my S, so the slope of this line is what we are talking of, and that is my secant modulus. Now, when it comes to the chord modulus, we say no, the origin is not the point which we are talking about, but we will take a point corresponding to the stress level of 50 microstrains, and then we use the formula delta sigma upon delta epsilon and use this to calculate the chord modulus, or this is the difference between the secant modulus and the chord modulus. The end point here is the same, but the origin when calculating the delta sigma and delta epsilon is different. In one case it is calculated from the origin, and the other case it is calculated at 50 microstrains. Coming to the tangent modulus, indeed by definition the modulus of elasticity of a material is the tangent of the stress strain curve, and as we can see in this nonlinear stress strain curve for concrete, the tangent or the value of the tangent changes depending on the stress level that we have. It is something here, it is something else here. So the tangent can be drawn at any point on this stress strain curve, and that slope will give us the tangent modulus. Coming to the dynamic modulus, it is also the initial tangent modulus. That is, we try to draw the tangent at the origin of the stress strain curve, and that is our dynamic modulus of elasticity. So if we take the real values as far as this particular stress strain curve is concerned, we find that the secant modulus is 24.9 GPa, the chord modulus is about 24 GPa, the tangent modulus is 18.8 GPa for the point at which we have taken the tangent, and the dynamic modulus, which is the slope of the stress strain curve at the origin, that is 34.9 GPa. Now this obviously is the highest, because we can see from the nature of the stress strain curve of concrete that is where the slope is the maximum. With increased application of load, the slope changes. We do not see much difference between the secant modulus and the chord modulus, and of course the tangent modulus will keep changing. So it is not a matter of which of them is true or which of them is false. It is only a matter of how we define it, and also keep in mind the fact that what is the range of the stress in which most of the structures operate. And there we find that most of the structures actually operate at levels which are lower than 30 to 40% of the ultimate stresses for most of the time, and that is the basis for using this 40% to define the point S on this stress strain curve and moving forward. We must remember that this stress strain curve is also a function of time. If we are talking of early age concrete, this stress strain curve will be very different. If we are talking of very old concrete, the stress strain curve will be different. It will also depend on the moisture conditions and so on, as we will see later on. So we should be careful in interpreting the results that may come along. Like in the case of the stress strain curve, in the case of the elastic modulus of concrete also, without having to go to the stress strain curve and trying to determine the modulus of elasticity experimentally, and to that extent evaluating the modulus of elasticity for a given concrete, for a given project, codes, whether it is the IS 456 or the ACI 318 or the SEBE FIP, they give us some kind of guidelines to say that okay, we can estimate the modulus of elasticity using these equations. So for example, the IS code says EC can be taken as 5000 root of FCK. The ACI tells us that it can be taken as WC to the power of 1.5 into 0.043 root of FC dash, and so on, where these parameters are defined here. So there is some guidance available to us even before or even without carrying out any tests to determine the stress strain curve of concrete, and then using that to formulate the modulus of elasticity. Having said that, we must remember that these codes are applicable only for a certain range of concrete at a certain age and so on. So we cannot use these values, for example, for very young concrete or very high strength concrete and so on. So the designers have to make their choice, and that is very important to appreciate that even though the code allows you to use these equations to estimate the modulus of elasticity and perhaps so many other parameters, we must make a judgment that indeed the estimation is within the range which was foreseen by the people who wrote that document. So having said that, so we should remember that these equations are largely empirical and should be used with caution. Coming to the kind of factors that affect the modulus of elasticity of concrete, there is a cement paste matrix, which could be the porosity of that matrix as well as the E of the cement paste. The ITZ, the porosity and the composition of the ITZ, the aggregates themselves, which is the porosity and the elastic modulus of the aggregates themselves, and of course the testing parameters, which could be the moisture state of the specimen, the loading rate and so on. So you will recall that all these parameters are very similar to the parameters that we talked about when we were talking about the factors affecting the strength of concrete. And before we close the discussion on the stress strain curve, let me just spend some time and talk about this curve a little differently. So now here is a stress strain curve which is linear. What it basically says that for a particular level of stress there is a particular unique level of strain and vice versa. Now if we look at a situation where this applied load is taken to a certain level and then maintained at that level, or for that matter the load is maintained at this level which is slightly lower than this level, or it is maintained at a level higher than this level, then what is the expected response of this material in terms of the strain? Do we expect the strain to not increase or decrease and remain at the level at which it was measured when the load was initially reaching this level or this level or this level? Now this is the idea of a sustained load. Now the action under sustained load is something different than under a monotonically increasing load. So the stress strain curve as we normally see, which is the kind of graph which I showed you like this is determined under monotonically increased. Do not wait for too long. How long we wait and so on, that's immaterial, and that's why in fact the codes tell us the rate of load application. Now once we talk in terms of sustained load and so on, we obviously have to talk about the increased strains under sustained loading. So now we talk of a strain over time. There is what is called elastic deformation, then there is something called creep deformation, and this is the total deformation. So this creep basically is the phenomenon that is increased deformations under a sustained load. So at a given point in time or a given point of load there is an elastic strain, and then if that load is sustained at that level we have the creep strain. In other words, what is being said is that this level of strain for this level of load is not necessarily the final strain under sustained load. So that strain is somewhat higher than this level. Effectively what we are saying is that slope of this line, whatever that is, if we somehow reduce this slope, so this value here would be closer to the total strain that we get if we consider the creep of that material in the deformation. Now this is something which is used in codes and specifications, and for example the Indian specification tells us that we can modify the modulus of elasticity of concrete to ECE using a creep coefficient which is given in the following table, and that is what it says is, in the absence of experimental data and detailed information on the effect of the variables, the ultimate creep strain may be estimated from the following values of creep coefficient, and the creep coefficient is defined as the ratio of the ultimate creep strain to the elastic strain at the age of loading. So in the case of concrete, it is also important to note that the extent of creep deformation would change depending on the age of loading. So if we are loading at 7 days, we can expect the creep coefficient to be 2.2, whereas if we are loading at 1 year, the creep strains would be only 1.1 times the elastic strain. So this picture here tells us how the creep strains will vary as a function of the age of loading, and the relationship that ECE is being taken as E divided by 1 by phi tells us how much will be the modification in the E that we originally used if we want to take into account creep effects. Continuing this discussion further, what happens that if this is what is our stress strain curve without creep. What happens if we unload? That is, we take the load to a certain point, keep it for some time, and then we unload. What is the response of the strain to this kind of a loading cycle? Now, the strain response over time would be similar to that when we saw in the loading cycle. In the loading cycle, we had elastic strain and creep strain. In the unloading cycle, we will have an elastic recovery which will happen immediately, and we will have a creep recovery which will carry on over a long period of time. Now, whether or not the recovery will be total, that is, whether or not there will be any permanent deformation, would depend on what is the material that we are talking about, what is the load level to which we had taken the material and then are unloading, and so on. So, in the case when the loading level is such that the material is in the linear range and we expect complete recovery, this is what we get here. In the same material, if the load has gone beyond this point, then of course we can expect this amount of permanent deformation. Similarly, in the case of material 2 or a different material, the amount of permanent deformation could be quite different depending on the material characteristics and so on. So, we are of course not discussing creep in a major way, we are not discussing permanent deformation in any great detail, but I thought a discussion on the stress strain curve of concrete would not be complete unless we have spent some time talking about creep, that is, in structures which are under sustained loading. How much is the sustained load in a concrete structure is a different matter. There are dead loads which are always acting on the structures. In certain structures, the dead loads in fact govern the design process, and that is why we thought that it is important to understand this aspect of the stress strain curve. This of course is the list of references and material which you could refer to, and I would like to thank you for your attention.